Welcome to video number 1 in this two-part series that provides one approach to evaluating human-operated products. While the tools and techniques demonstrated can be used to evaluate any human-operated product, a motorcycle was chosen for this demonstration because of the amount of movement required by the operator. For example, one of the key tasks for motorcycle operation is changing direction. This involves rotating handlebars using fixed position hand grips that must be far enough apart to provide stability and leverage, but also positioned so that maximum rotation of the steering assembly does not exceed operator reach, while the operator may also need to lean and even shift position in the seat depending on cornering speed. In this video, part 1, royalty-free motorcycle geometry obtained from TurboSquid specifically for this demonstration is prepared for evaluation using tools and techniques that both enable and restrict the range of motion for the steering assembly and overall motorcycle lean angle. Part 2 in this series will demonstrate a rigging technique that can be used to predict human behavior for a variety of riding scenarios that leverage these range of motion restrictions. The topic today is range of motion limits for imported objects. For that, I'm going to grab some motorcycle geometry we got from TurboSquid. And as often happens, we don't have a whole lot of details. So we oftentimes have to figure stuff out on our own. And there's lots of tools inside the software that can help. Here we've got the steering assembly, and we've also got the everything else. And if you'll look at the steering assembly, you'll notice that its reference point is not really conducive to the way the steering wheel would operate if it was, if it was a real object. What's really supposed to be happening here is there's a shaft through here that goes into this little area here. There's a bearing in there, and then that would rotate on that axis, right? So how do we figure that out? Well, let's just go ahead and do it. We don't need this. All we need is access to this. So the first thing we need to figure out is, what is this angle? And the nice thing about computer geometry is there's these surface normals. Not really the topic for the discussion today, but these surface normals have to do with how light scatters when it hits a surface. And these surface normals are perpendicular to the plane. And so we can pick up that information. And we do that through what's called a contact point. And all you have to do is drag this contact point onto the surface, and you'll notice that it's picked up that surface normal. So there it is. I don't really need that to be a child of the rest of this geometry. I just need access to that. This is just a vector. Looks like we're off by some minuscule fraction of a degree there, but that's the orientation of this device right here. And so we're going to use that. But we also need to know what the center of this device is, and we don't have that information either. So one of the things we could do is we could measure it, or we could let the software take care of it for us. So what I'm going to do is I'm just going to put my mouse cursor as close to the edge as I can get and add a marker. And then I'm going to do it to the opposite side. And you can see these pointed things are kind of nice because there's one on the opposite side, so I can reference that. So here you go. Now I've got two markers. Again, these don't need to be children of this geometry. I just need to have them both selected. And then under the Tools menu option, I can go to the average location, which does a variety of things, which we can talk about later. I'm going to add those to my group, and then I'm going to generate a new one that'll be the average distance between these two things. So that's my new one, and that's the center of this object right here, referenced by these things. I might be off by some fraction of a millimeter, but close enough for the purposes we're talking about. Again, I don't need this stuff anymore, so I'm just going to get rid of it. So that's my reference point. So I'm going to call it reference. So there's my reference point. That reference point is not pointing in the same direction as this one because we didn't worry about the orientation. We were just worried about where the center line was on the surface. So we need to take this orientation, and there it is right there. So we're going to copy it and paste it into the rotation value here. And now they line up. Now they're parallel. So this is located the center of this bearing, and it's also oriented correctly, and I didn't have to work too hard at it. Now what do we do with that? First thing I'm going to do is just kind of move it out of the way. Nobody's going to look down here, so nobody will ever see it. And then I'm going to bring my steering assembly back. So there's my steering assembly. So what I'm going to do is I'm going to make my steering assembly a child of this reference point. And I can do that inside here, or I can do it in the interactive window. It doesn't matter. So I'm going to right click here, and I'm going to go pick parent. Here I'm going to pick this. And this is a child of this. So if I rotate this, it rotates correctly. But you'll also notice it rotates freely, which isn't very realistic. There's some range of motion limit associated with the steering assembly, and we can set that up as well. So let's do that. Okay, so that is my reference point. But what I want to do is I want to create a node under there that we can restrict the range of motion. And so I'm just going to use a cube. It doesn't matter what it is. You can pick anything you want to. I'm just going to take a cube. I'm going to drop it in this world, and I'm going to make it much smaller. So let's go 0.05, 0.05, 0.05. So there it is right there. There we go. I'm going to make that a child of this. And the reason for that is because then I can work with this object. If I orient this object to 0, 0, 0, because it's a child of this, that'll be in reference to this orientation. So watch what happens. If I set this to 0, it's oriented exactly like this object. If I make it global, now it's again oriented the same as this object. But if I make it a child of this, then its position, rotation, and scale are referenced to its parent. So now it's referenced to its parent. And that object, oops, by the way, this allows you to interactively pick nodes lower than the parent. So interactively I can pick this. If I select this, then I'm always picking the top level node. Like that. Now you can always go inside the expert pane and pick whatever node you want to. But interactively, that's the difference between these two selection options. So I'm just going to set it over here so I don't forget. So that's that object. If I see its orientation is 0, but its position is different, and that's also referenced to this. So as I get closer, you'll notice that this number is decreasing because it's closer to its parent. If I set it to 0, it coincides directly with its object. But I'm going to put it just a little bit lower so I can get to it. Doesn't matter where it is. I just need the orientation, and the position needs to be along that blue axis or the z-axis of that object. So when I rotate this thing, watch its rotation values. They're relative plus and minus to the parent, so they're really easy to work with now. And we have this rotation clamping option in the expert pane. I'm going to open that up. And let's say we know that this particular motorcycle has a 27.5 degree rotation to the left and a 27.5 degree rotation to the right. So that's the total rotation. I made that up. So what I'm going to do for the minimum rotation is I'm going to go minus 27.5. And for maximum, I'm going to go 27.5. So plus and minus 27.5. Those are the mins and the maxes. Now you'll notice that it hasn't really taken effect, and the reason for that is because the constraint, the rotational constraint for this blue axis or the z-axis, if you ever forget, these are color-coded and they tell you which one's which. This is z-axis right here. The z-axis has not been enabled. It's false. But if I enable it, now it's true, and it's restricting to plus and minus 27. But I can still rotate about the x-axis, or this red axis, and the green axis, or the y-axis. And the reason for that is because those are off. So if I turn all of them on, then this object will only rotate along that axis, and it will be restricted to the minimum and maximum values shown here. So if I set this back to 0, bring our steering assembly back in, and make the steering assembly a child of this cube, when I rotate this cube, it will respect the range of motion limits. I've got a mechanical system that reflects what it actually would be in the real world if you were to create it. And that can come in handy when you're evaluating an object. Let's do it again. This also applies to translation, but I'll leave that to you to play around with. Works the same way, but what we're going to do is we're going to see the ground point, the contact point of this front tire, and use that as a lean angle minimum and maximum, because maybe in our evaluation of the usability of this particular design, we want to know what the minimum and maximum is, and we don't want to type it in. We just want to interactively set those things up. So the first thing I need to know is I need to find out where is this tire going to impact the ground. And again, a lot of times you just don't have that kind of information when people give you geometry. So I'm just going to use a cube. I'm going to set its position to 0, 0, 0. And I'm going to use that to figure out where the contact patch is on this tire. So now whoops. Now I know. See how close we can get it. Yeah. This is symmetric, and so those two little corners there are probably equal distance apart. And what could we do to utilize that to find the center point? Well, we can do what we just did with that steering assembly. We can right-click on this little corner right here, and we can add a marker. And then we can right-click right here. Let's make that invisible. And then we can right-click right here to pick the other point. I've got these 2 points. And I can go back to my average location tool, add those to the list, and generate a new one that is half the distance between them. I don't need these anymore, so I'm just going to get rid of them. And I have a contact patch. So that's where that is. And I'm going to name it reference tire contact point. And I'm done with this cube. I can make this steering assembly pivot relationship a child of this, and I can make this, the rest of the bike, a child of this. And then I can lean them both over. Both of these are children of this contact patch. And we could rotate it. And then we could go down to our reference pivot point and turn the wheel. And that turns correctly. If you wanted to restrict the range of motion of this, we'd have to do the same thing we did over here, but I'll leave that to you to go back and see what I did and replicate that, because you'll need a piece of geometry to use the rotational clamping. But we've already gone through that, so it should be easy. I'll leave it to you to play around with that a little bit. And hope you enjoyed this video. And what's up next is a demonstration of how we use these kind of things in the analysis of equipment.